Mic test. Hello and welcome back. So for this stream, I will solve this particular LeetCode problem. I haven't solved it before, but I know that this is a dynamic programming problem, and I mean there are multiple solutions, but the idea to make this stream is to explain the entire process and thinking behind solving any dynamic programming problem. Okay, let's start. Zoom in a bit. Okay, fine. You're given a zero-indexed integer array nums of size n containing all numbers from 1 to n, and we need to return the number of increasing quadruplets. Quadruplet of 4 indices I, j, k, l is increasing if it is in a sequence from left to right, and the numbers are also increasing at those particular 4 positions, and we need to count, right, a number of increasing quadruplets. Constraints are fairly small. This can be possible. This is possible to solve in n square log n or even n square in some cases. So first I will go over that approach. We'll submit it. We'll try to optimize it at the best that is possible in considering all the possible choices that are I mean, whatever advanced techniques and data structures that we can use, we will try to optimize this to the fullest and not just try to get accepted for this. Fine. Okay, the question is fairly straightforward. Let's move on to some of the things. So we are given an array A1, A2, A3, A4, all the way up to, let's say, n minus 1 an. Let's say this is one best indexing, and there would be some 4 indices. Let's say these are the 4 indices, and we need to count the quadruplets of these 4 indices, I1, I2, I3, I4, such that they lie one after the other in this manner in the sequence of given array, and as well as the corresponding values at those positions are also increasing from left to right. This is the condition that we need to check for all possible quadruplets, and for all the quadruplets where this condition is valid, we will take it as a count of 1 and do this for all the possible indices I1, I2, I3 and I4 and sum up all the counts. That would give us a order n raised to 4 solution, because there are order n possible values that I1 can take, I2 can take, and I3 and I4 can take. So in all, if you have to consider all possible products of their individual values that they can take, it would be resulting in order n raised to 4 solution, which is not feasible, but yeah, that is one of the solution. And let's try to build up from this. Let me try to go over the ideas for solving any dynamic programming problem. So we are always constructing something in a dynamic programming solution. So we are always having some construction, and let's say this is some mathematical representation of the thing that we are computing. So in this case, we had a construction of 4 indices I1, I2, I3 and I4. So here construction is a set of 4 indices. This is what you need to come up with whenever we are solving any type of DP problem. And once you know what we are actually constructing, you need to know what are the constraints of that construction. So in this case, the constraints are that, let's say these are the 4 indices I1, I2, I3 and I4 that we are trying to construct, and the constraints are obviously that any index I should be in the range of 1 to n for one best indexing, or 0 to n minus 1, and the constraints were I1 less than I2 less than I3 less than I4, as well as the corresponding values in those array, in that array, should be increasing, right? You know these are derived from the question. So these are the constraints that will be given in the question, or you may have to even derive it depending on what type of problem it is. So this is given, and you figured that out, that we need to construct a set of 4 indices. Some things you need to figure out, some things they are already given in the question. So yeah, now you have these two information, construction and the constraints of those construction. Now you need to start constructing this, which is a set of 4 indices. Now whenever you have a large set of values that you need to construct, in this case we have 4, you need to start somewhere, right? You need to say that the first I am giving all these possibilities to a particular index I1, I2 or I3, anything. So next one is to start constructing. So these are not any formal definitions, these are just the conventions that I have been following. So don't take them this as any hard or fast rules, but this is just my own technique. So we know that we need to construct I1, I2, I3 and I4. So first of all, if we are going to construct these values from left to right and they need to be increasing, so it is always better to start here. And all the values that this index can take is 1 to n. Then you construct this, this and this. But you notice that if you forget what you have chosen as I1, let's say I1 was chosen as 5, and let's say you choose I2 as 3, which is invalid because you need to maintain I2 is greater than I1, right? So this gives us one more thing that we need to consider, which is the states. States are required so that you don't construct an invalid construction, and the constraints need to be followed for any construction that you are trying to create. So states will store what all value is important. Let's say these are the parameters which are required to make this construction that we are creating it should obey these constraints. So to make sure this construction obeys those rules, we need to keep some of the states, right? So let's see what those states would look like. So states mean any information that is required to obey these constraint rules, right? So if you have chosen I1 as 5 and let's say now you need to choose I2, you don't know what you should choose here, but you know that previously you chose I1 as 5 and the only constraint that I2 needs to follow is that it should be greater than I1. This was the first one, and the second one was the value present at I1 was less than value present at I2, right? These are the only two things that I2 needs to consider while going over all the possibilities. Hence, and these two, you don't need to store both of these values because a of I1 is derived from I1 only. So if even if you just store this index, which was the previously chosen index, in the state, then from that you can easily say that, let's say we know that I2 can take values between 1 and n, but it can only take values which are between this and I1 plus 1 to n, because this constraint is to be followed. Now you, based on this condition, if you know that the state has I1 which was previously chosen index, then I2 can search or try values in this range. So keeping the state helps us to figure out or to initialize valid possibilities for any index. Now notice that we don't necessarily need to store now we have we have given some value for I1, I2, and now we need to give some values for I3. Now you say that if you say that we need to store both of these in the state, then that would be wrong, because the only constraint that I3 needs to follow is it is less increasing in respective of indexes and increasing in terms of those values. And notice that if you have uh, chosen some values for I1 and I2, then this constraint is already fulfilled. This constraint is already fulfilled. Now whenever you are trying to give some values for I3, let's say we were saying initially it should be between 1 and n, but it should be between I2 plus 1 and n, and this gives us that it should be between I2 plus 1 and n. And only thing that it needs to follow is whether it is greater than I2. So I3 does not need to know what are the values of I1, right? So this makes sure that we only need to know the previously chosen index in the set, and only this should go in the state of the DP solution. Now once you have some of the states and you have you're trying multiple values for each of those construction parameters, which were I1, I2, I3, I4. Let's say there were some values that were given to I1. Let's say this. Now this resulted in some more values for I2. Then this resulted in, let's say, these many values for I3, and from here let's say the branch reaches out something like this. Now what I'm trying to explain in this is, so now you have the states that you need to store to create a valid construction. Now you also need to know whenever we are moving from this index to this or this to the next, what should actually be computed. So next thing is evaluation, right? Now to evaluate, notice that we need to construct the set of 4 indices. Are we complete when we assign a value to I1? No. Are we complete when we assign value to I1 and I2? No. We are only complete when we have assigned the value for all of these 4 variables. So once we have assigned the values for all of them, that means that we have found one way or one quadruplet. I think it should be quadruplet only, and it is a valid one. That is more important, because validity is already being considered while we are trying out the possibilities for each indices based on what was the previously chosen index position. Now any transition graph always results in a directed graph. So what we saw in the previous slide, it will always be a directed acyclic graph. This is the most important property for to solve any dynamic programming solution, that this graph should be a directed acyclic graph. Now notice that this graph will have structure something like this. So it will have some values given to I1, I2, I3, I4. Let's say these circles denote what all values are given to I1, and these are the values given to I3. I mean, there would be exactly n of this, so this should be n, but just for the sake of simplicity and not trying to make it too complex, I'm trying to keep it simple. Now let's say you gave some value to I1. Based on this value, you gave some value to I2. Not some, but there could be multiple values, right? Now these resulted in this resulted in this resulted in something like this, let's say. Now for one particular iteration or one particular assignment of values to this four indices I1, I2, I3 and I4, we will end up at this position, and we don't need to do any more assignments after this. And if you trace back this, right, this will be the values that we have given to I1, I2 and I3. And you can see that this is one path from this node to this node. So this is one path, and obviously one path means one assignment of valid values to this set I1, I2, I3 and I4. Right, now the problem here is you need to do this for all of these ending indices, and notice that this may end up, this will have multiple branches, and basically we need to count the number of ways or the number of paths from any node which starts here and any node which ends here in this graph. But you don't explicitly create this graph, this will be taken care by the transitions. And from these transitions I will also explain what are we actually evaluating and how the recurrence function will look like. Now if you have to write a function which stores the states, so let's say we are currently at index I, and let me first try to create a diagram so that it is easy to understand. Now let's think of it like this. First we had to give some value to I1. Let's say we gave this particular position to I1. Now after we are given something to I1, we will try to give I2 any value which is to the right of it, any index which is right of it, and obviously this condition will also be taken care when we are doing that only. So let's say this was I1 then I2, and when we were trying to wait, we are actually understanding the transitions, right? So we gave something to I1, and there could be various values that I2 can take. Now it could be this. Now notice that the number of ways of assigning I1 and I2 would be 3, because this is the first, this is the second, and this is the third. Hence, if we have to write a function which counts the number of ways to assign this value from left to right, which will be something like this. Suppose we are at index I2, we want to give something to I2, and we have previously given something to I1. Let me write a better. So let's say f is the function which will give us the number of ways to construct a valid sequence of 4 indices, and let's say currently we are at index I. We haven't chosen this in the construction, we are just at index I, and we're saying that whether we want to choose this or not. and obviously it should be greater than I2, and we know that previously we chose I2. We have assigned values to I1 and I2 until now, and we are at some position which is I, which is greater than I2, and according to the states that we saw, we are also storing this. Now there are two possibilities: either to take this index in the sequence that we're constructing, or don't take. This is the first and second, and we always go over all choices whenever we are constructing the dynamic programming approach. We always consider all the possible choices that are possible, right? So if you are at index I, there are two possibilities: either it will be used in the construction or it won't be used in the construction. Now if it is used, then that means this I2 will have been in this transition, and the number of ways to do this would be the number of ways to go from I2 to I, or I mean I2 is, no, it should not be I2, it should be, since we have chosen I, now anything that is to the right of it can be chosen, hence the last chosen is I. And if we don't choose it, then that could be other possibility. In that case, it would be chosen from, we have skipped I, right? So we could have started from I plus 1. And notice that the number of ways to do this is the number of ways to do this plus the number of ways to do this. And to understand this, why is it a summation of number of ways, you simply say that you need, if you want to count the number of paths which grow from, wait, let's say this is the number of nodes, this has a graph like this, right? So let's say we have 3 nodes, there are 3 paths to go from node 1 to 2, and there are 2 paths to go from 2 to 3. Now if you want to count the number of paths to go from 1 to 3, then how would you do? It is obvious that you choose any of this path and any of this path. So that would mean 3 choose 1 multiplied by 2 choose 1, which results in 6. But this is not directly obvious. These counts are not given to us whenever we are solving dynamic programming, these counts. So you need to know the intermediate results for each of this. So first we will find out, we know that there is only one way to arrive at this node. Then we count the how many ways to arrive at 2. If you know that, then from that we will count the number of ways to arrive at 3. So to count the number of ways to arrive at 2, we say that any of these paths can be chosen, and there are 3 of those. So number of ways to arrive at 2 would be all the ways from which we came at index 1, and for all of them there would be 3 more ways. Right, so there was one way to come here, and from there, so number of ways to do that would be 3 times number of ways to arrive at 1. And this 3 is multiplied because it is actually we should say it something like this. So let's say this was h1, ha, hb, and hc. Then let's say in the first of possibility, we traverse some of the path to come at a, and then we choose edge a. In that case, we have chosen one way, hence it is the number of ways to arrive at a multiplied by one way, and the same for hb and hc. This is 3 times that value. Now you have computed ways of 2, then you need to compute ways of 3. Ways of 3 would be 2 times ways of 2. This 2 is a summation for all of these values. To understand this further in terms of dynamic programming, we have I1, I2, I3 and I4. We assign some value to I1, then we assign some value to I2 based on what was assigned to I1. Now these edges are actually transitions. Now each transition is a edge, and number of ways to arrive at this. Let's say this is a position A of set of indices, and this is B. Then ways to arrive at B would be summation of ways to arrive at A over all the transitions. Right, which would be the edges if you consider them explicitly. Now this is what we are trying to figure out. Now until now we have understood what are states, what is a transition. Now let's understand how do we evaluate that. From this diagram we understood that we need to take this sum for each of these transitions from this to this, so that the ways are calculated appropriately. So we understood the recurrence was written here, right? We stopped here. So now we know that the this assignment is actually a plus, right? It could be product or it could be something else based on different types of problem, but it is important to understand what we are evaluating and how it is computed, how it actually works in terms of the transitions and the in graph terms. And this was the first choice, to take I, and the second was to don't take it. In that case, we start choosing indexes from I to I plus 1. We tried I. If we don't take it in second choice, we make choices for I plus 1. And since we have not taken this, I2 still remains the previously chosen index of the construction. Okay, that is good. Now let's move on to recurrence relation. For this I will give the top-down or recursive functional definition. So let's say f function denotes the count that we are actually computing, which is same as the number of constructions as we saw here. Now we start at, let's say, some index I1. And since I1 can take values between 1 and for one best indexing. Then we, after choosing some I1, it will be stored in the state, and we need to choose from I1 plus 1. So 1 plus 1 I1. Let me also denote what these say. So this is the next index, this is the previously chosen index of construction, and this is a possible index. We are trying to make choices for it. It is not necessarily included at this moment, and we need to do it for the two choices, which was f of what was it. For now, let's say this is I1. I mean, let's say this is ID and this is I1. This choice was to consider it in the subset, and we need to check the constraints. After checking, if it is valid, then it would be index ID plus 1 and ID. This becomes the last previously chosen, and this becomes the next searching index. And if we don't want to take it, then this transition would be f of ID plus 1 to I1. Now this is simply the sum of both of these values, and this is how we arrive at a recurrence relation. So let me write it in more clear format. We wrote that f of ID, and for now I will use the previously chosen index as previous, is f of ID plus 1 ID, or f of ID plus 1 and previous. Perfect. So this is the recurrence relation in top-down format. This can be evaluated in order n square time, because there are only two transitions, and there are two states which each of them take order n unique values and multiplied by a constant, which is resulting in order n square solution. First, I will implement this, we will submit it, then I will move on to the next thing, which is time complexity evaluation. Of recursive functions, recursive TP approach, and I will also go over time complexity for non-memoized recursive DP solutions. So I'm just writing this down so that I remember that I need to do this as well. So yeah, let's make it to do. Okay, fine. Let's go over the implementation now. Where is the question? Okay, start the terminal, zoom in. I think this is still very small, but yeah, fine. I hope this is fairly large on small devices. Let's take this boilerplate. I have this repository, and Let's make it sol.cpp, and this is the function. Perfect. Let's rename nums to a. Since we are going to write a recursive solution, we need to keep this as a private variable. I like to keep it like in that manner, so that this of a is a, this of n is a dot size. Done. Now we will try the values for I1, which was, I have also missed out some of the cases, which was base cases. I will implement this and then we will go over that. First I need to give some of the values for I1. So let's try I1 equals to 0 to, and this would be answer, and since it is one assignment, we need to count the number of ways for all the assignments that will be performed after given I1, I2, and I3, and so on. And this means that the function, I like to call it go, has chosen I1 as its previous index, and the next indexes that it can take should be from I1 plus 1. Let's write that function now. Long go current index previous index. I will write base conditions. Before that, the number of ways is initialized. Return from here. Now there are two possibilities. So first one was, let's say choice one. It was only valid, and this choice means that consider a of current in the construction. And the second one was don't consider, right? This is only possible if a of current is greater than a of previous, and then only we initialize that variable or assign a value to it, which was what. So this is id is current, so it would be current plus 1, and current is the previously chosen index. Now this is the case, and in case of choice 2 we don't have any constraint that we need to consider. It would simply be current plus 1 to previous would still remain same, because we haven't said that we need to choose this index, and the total number of ways is again choice 1 plus choice 2. Done. Let's try it on the samples. Okay, what for the samples? Are we not given that value? Okay, yeah, we are only given the array 1, 3, 2, 4, 5. And 1 2 3. I think we have solved another question. I was thinking that I is less than j is here as well, but it is, I mean, I have solved a different question. Okay, it's fine. I will just, I cannot submit it because it will be wrong for this. Thing that I've done is I've assumed that this is an increasing sequence and those indices also lie. I was assuming this should be j, this should be k, and this should be l. Okay, fine. I will extend this approach only. I mean, I have almost completed that, but the answer for the second test case should be 1, and for the first should be 2. Let's try it. I forgot the base cases. There is one more thing that we have missed, which is the number of indices that we have chosen. If you don't know that, you can choose up to n values in the subset. So if we are at the final index, let's say if even if count is greater than 4, we said that there is no way, we don't want to consider that. And if we have reached at the end, the count should be 4. These are the cases. In this case it becomes count plus 1. In this case it remains the same because we haven't added anything. Let's try. 2 and 1. Okay, this works fine, and this is a exponential solution because we haven't memorized it. If we have to do that, we will do something like dp of 5 n and n. Let's say this is 1000. You will have to set dp minus 1 dp, and here we check whether this particular state is visited. If it is not minus 1, then we know that this is visited and we can return from here, or else we compute it. The answer should still be 2 and 1, but the time complexity now is order n square. This should be because I haven't set the stack size limit. Okay, looks fine. I mean, there is no use of submitting this or anything, but okay, let's try to solve this problem further. Okay, I want to explain these two, right? Time and base case. Okay, for the base cases, let's understand base cases first. In this problem, we had I1, I2, I3 and I4. And notice that when I added a new parameter called count in the recursive function, after I've chosen I1 it was 1, after I've chosen I2 it was 2, after I3 it was 3, after I4 it was 4. So whenever this case is occurred, that means we have successfully assigned indices to I1, I2, I3 and I4. That means the it should be counted in the base case. So this count, if it is 4, that means we have found out one way from the solution. And if it would have been greater than 4, then that means we have chosen some value for I5, and which is not something that we want to consider. So there we have written 0 as you saw in this code. And the other thing was, if we only choose I1 and I2 and still we have reached the last index of the array, in that case also we have partially selected the values for the construction, and that should also not count in the valid way. So notice that if we have exhausted the indices and we have exactly 4 of them in the selected indices, then only then one way is considered. So these are the base conditions, and depending on different problems you will have to implement them accordingly. Next thing is to understand the time complexity. Whenever you are writing a recursive function, let's say for example Fibonacci for 3 terms, f of n minus 1 plus f of n minus 2 plus f of n minus 3. First you need to create some transition graphs. From n you go to n minus 1, n minus 2, n minus 3, and from each of these subsequent nodes you have 3 values that you go to. And whenever I'm in go to, that means this state is visited by a function, by the whatever you call recursive function call, right? Now to find out the time complexity of a recursive approach, if I have to expand this further, notice that each node will have 3 transitions for each of them. This now the time complexity is saying that if there are 1,000 states that were visited, then we don't never explain time complexity in terms of hard-coded values, but if there are some states visited, let's say x amount of states, then the time complexity is at least order x. And if there are x states visited for a particular n, and notice that to go from one state to other we have 3 choices, so you need to consider this as well. So the time complexity is usually formulated as number of states visited multiplied by transition cost. Now let's do one thing, try to copy this. Here, Okay, fine. We are here and I need eraser. Since I gave the formula for time complexity of recursive solution, so always remember this. Now notice first, let's try to find out the number of states that are visited, and the transition cost is 3 because there are 3 transitions. So notice that finding out the number of states would be same as finding out the number of nodes. So in this we have only one node, in this we have 3, in this we have 9, because each of them will be multiplied by 3, and those many number of nodes would be new states. And this would be 27, this again would be 27 times 3, and so on. So notice that for any n, the number of visited states is sigma I equals to 1. I mean, it is, what was it? I raised to, sorry, 3 raised to I equals to 0. And this sums up in a geometric progression which will have a value of, I mean, how do we represent in this in terms of n? I mean, there would be n levels of this, right? Because notice that this leftmost branch will always have one number less, and this should eventually go to 0, which is, let's say, best case. So this height is order n, or exactly n. So this should be n. Now the sum of the GP, which has the first term as 1, common ratio as 3, is, I think it is a raised to, let me search it up. First term times r raised to n. So the number of visited states is first term times r raised to n minus 1 upon r minus 1. And n is the number of terms, and we have n terms here. So this would be 1 times 3 raised to n minus 1. Common ratio is 3. This would be 2. So this is in time complexity terms, this is these many number of states that are visited. And like I said, the time complexity is same as the number of visited states multiplied by transition time, which still results in this exponential value. So this is what you need to understand whenever you're trying to figure out the time complexity of recursive solution. Since this is exponential, it is unfeasible and non-feasible, and it will take a lot of time for any input which is, let's say, greater than equals to 15. After that, it will be exponentially increasing. If you look at the graph of any exponential function, or 3 raised to n in this case. Now what magic does dp do to reduce the time complexity? How does dp reduce time complexity? from which was 3 raised to n, and we made it order n square. So how is that possible? What was that magic? Notice that whenever we wrote recursive function, we said that the time complexity is number of visited states multiplied by transition time. And for now, let's say this is constant and we forget about this. So the number of visited states, if you don't memorize this, should be 3 raised to n. But what dynamic programming does it memorizes states. That means, if you saw the recursive breakdown, notice that each branch had 3 sub branches. Now some of these would be common. Maybe this was equal to this was equal to this. So there are a lot of duplicate states visited. Again, some of the states are visited again, and the only thing that DP does is it memorizes a particular state. So that means the number of visited states would be same as number of unique states. Now visited state is very different and unique states is very different. Notice that if you have started with n, and you will essentially go to 0, and all the values that these nodes can take is only order n, right? So we basically reduce the time complexity for this is for this problem, which is Fibonacci. Where did it go? Okay, I was explaining this for a recurrence relation, which was something like this: Fibonacci with the last 3 terms. So for this, we had original recursive time complexity order 3 raised to n, but for recursive memorization with dynamic programming, we changed it to order n by memorizing all the states. And since any state is visited only once, that means if any state is visited only once, then that means the number of visited states is same as number of unique states. And we will not go over some state once again. So this gives us n possible values. Now if you have to transfer this to our problem, the recurrence relation for our problem was this, okay, which was f of id previous is of id plus 1 id plus f of id plus 1 previous. Now for the Fibonacci problem, this node had a single integer in it, so you could have guessed what are values any states can take, which was, if there was n, then any of these node can take value between n to 0, 0 to n. But since we have 2 numbers in this state, right, now there is a state which is of 2 parameters independent. Hence the number of unique states would be the number of unique values that the first takes, let's say u1, multiplied by the values that this takes. There is multiplication because let's say there are these values that id can take and previous can take, this is 3, 4, 6, 7. Then collectively they will take a cross mapping between each values to every other value, resulting in this product. Hence there were n values for this and n for this, hence the number of unique states was order n square, hence the time complexity, obviously multiplied by the transition factor, but since it is constant, the time complexity becomes order n square, which is the number of unique states in the graph. And if we would have kept the recursive solution running, you would have to do it something like this. So there is a state which takes two values and there are two transitions, each of them results in these two values, then again there would have been split. Now this will take one value, 2, 4 and so on, and collective values that any node can take will be order n square unique values. So that exponential term would then become something like 2 raised to n square or something. You will have to figure that out, but it is some exponential factor. So this is how you find out the time complexity of a recursive as well as a Memo STP solution, and this is how you differentiate between them to solve it for any problem in general. We also looked at the base cases, the implementation. There are multiple ways to solve this. There was one mistake that I did in the stream was I took this problem but solved a different one. There could be another solution for this, so we need to think on that. That's it for this. I hope this was helpful. Do let me know if you have any doubts or suggestions. Thank you.